couple of words before. So this was this work kind of tied with previous work, developing this physical model, and we want to know whatever we get, is that good enough or not good enough? And it was done with the support of Bushfire CRC, and I did this work with Marty Alexander, retired from the Canadian Forest Service. We are here celebrating the 60 years of fire research, earlier work from Alan MacArthur, and since that time, since those earlier models, a lot of models have been developed, and almost every year new models are developed, and you really need to know how good these models are. And let me make when I talk here about the model evaluation of rate of spread model evaluation, I'm talking about the equation that determines how fast the rate of the fire is going to spread from point A to point B, right? I'm not talking about fire spread simulators. Fire spread simulators evaluation of their performance is much more complex because there's much more things in between. So we are going to the simple scenario of a fire spreading in a straight direction, and you want to know how good the prediction is for what you observe in terms of rate of spread. There's a lot of ways to look into model evaluation. A lot of people like to do sensitivity analysis, look about how the models predicting extreme conditions, things like that. And there's even people that think that we cannot evaluate fire behavior models just because fire is such a variable phenomenon. But when you think about building models to be applied to support decision making, to know how fast the fire is going to go, is it crowning, is it a surface fire, how far go the spot fires, if you want to use those models, we need to be able to evaluate these models, right? And I have been developing models for some time, work with Wendy and others, and we always want to know when you do something, how good is this? Is this better than what you had before? Is it not better? It's just so always been in the back of my mind every time I do some kind of modeling exercise. Want to know how good it is. And as I said, there's a lot of ways to look into model evaluation and model uncertainty. The way we did this study is a very, very simple way, is that we went to the literature and collect all the studies we could find where model predictions were compared against independent data, fire spread, from field observations, right? The source of data were several: wildfires, sky burns, accidental fires, and we put a few constraints. A study to be included need to have more than 5 fire predictions, so there will be a bit of a substance in terms of statistics. And it needs to be a wide flame front, because we know there's a bit of an effect of flames, of fire size. Is it spreading in steady state or not? So put those constraints. We searched the literature and found 49 studies where 49 different studies where there was this kind of model evaluation. Most of them in North America. About 1/3, a bit less than 1/3 in Australia, a few in Europe, a few in Africa. These are the fuel types we found. 6 of the studies were grassland fires, 9 shrublands, conifer forest, the bulk, 17, 9 eucalypt forest, and then other is flash fuels, deciduous forest, mixed wood forest, and things like that. And in total, we found about 1,300 direct comparisons between a fire prediction and observation. Right? Quite a large data set when you think about this. So then from this, there was way more data than we thought we would find. From this, we we put these questions. First question was, how accurately can one expect to predict the spread rate of a bushfire or wildfire with current available models? Right? There's also a question when you do the FBAN course, get the perspective of the user, see what's your expectations? You think that 10% error is too large, or 50%? Or, you're quite picky on a less than 5% error. Another question we thought we could answer with this is, are wildfires inherently more difficult to predict than sky burns or an experimental fire, right? We tend to think about a wildfire, this big, bad, big fire that is unpredictable. And we did data set, let's look into this. Let's see what errors we get in wildfires and in other types of fires of lower intensity. And then was the last question was, can we come with all these data set, can we suggest an acceptable error for a fire behavior prediction, right? Nobody else has done it before, so we might as well do something about that. What are the metrics we used in terms to evaluate or judge model performance? We look at the mean absolute error. So we put all the errors together, absolute terms, so the negatives and positives don't cancel each other, and get an average error. We also express it as a percentage. Errors that maybe is good to compare different data sets with much different rates of spread, and then the bias. So here we have two examples of two fires that you see predicted on the bottom axis, observed in the y-axis. We have a line of perfect agreement, so normally we want the data points to be in this line, that's the good thing. These are all wildfire data sets. We see quite high rates of spread. Important to consider also here in terms of bias is that if the data comes in this right-hand side of the line, it's an over-prediction. Maybe it's not too bad, over-prediction is always safe, but what's really bad is under-prediction, right? We don't want to have under-predictions. That put people and resources at risk. Two different data sets, two just example. In this case, you see all the data on the left of the line. It's a bit quite an under-prediction. This model is not really good, right, for this data set. And the other one, the data is pretty much, you see a lot of spread. You might say it's a lot or not so much, depending on your perspective, but if you kind of follow the line of perfect agreement, there's a bit of an outlier, but it's not too bad. In terms of these two data sets, one have an error of 42%, second one 54%, just slightly more. Bias, the bias is equal to the error, not too good. Here the bias is slightly over prediction bias because of this outlier. So this is kind of the data we are playing with, right? Example of what are really good fits. We have bottom grass moorlands data and also data from WA Miley, work that Lockie McCaw did to evaluate the Rotterdam model. This was the lowest errors we could get in the data set, 20%. Not much of a bias either. And also moorlands, pretty good fit to the evaluation data set. So again, all these data we use are independent of the model. So it's like totally independent validation. These are examples of what we don't like to see. This is work from also Lockie, Jim, and Phil, looking at using the Vesta experimental fires and looking how existing models predict fire behavior in the Jara forest, right? And you have the Red Book and the fire danger mirror, and we see a lot of under prediction, right? And this was, when this was done, just came to confirm what was thought to happen, and that's why Vesta was conducted, one of the main reasons, right? All right, well, when we put all these data sets together, this is what we get. In terms of average error per studies, we have 7 studies with errors less than 30%. And when we have considered less than 50% error, with about 1/3 of the studies, so 16 out of 49, 1/3 were error less than 50%. The bulk of data, more than half of the data, had error between 51 and 75%. This just gives you an idea how well we can predict fire or rates of spread, right? Another thing that was interesting was most of the errors were under prediction errors in these models. This also reflects when you look at the data, things have been evolving through time. A lot of these are testing old models that tend to overpredict, and now we get better results. Also to note here, an under prediction is bounded between 0 and 100. If it's an under prediction, you can never get more than 100% error, right? But when you have over prediction, you have an open scale. So that kind of put the context of that first question, how well we could predict fire. Second one was, are wildfires more difficult to predict than experimental fires or prescribed burns? And when you look at the errors, in this case we have prescribed fires, experimental fires, and wildfires, and we have errors by under prediction and over prediction. For under prediction, the errors are pretty much the same, so there's no difference in terms of capacity to predict wildfires. And in terms of over prediction, errors were lower in wildfires, right? A bit surprising. But this is also when we put all the data together, right? Let's look at some specific cases. And also, another question we have, when you do models based on these small fires, experimental plots, there's always people that ask, well, how can you expect a model based on this to predict something like this, right? It's a fair question. Is this realistic? Are we able to replicate the process here that happened here? First glance, I wouldn't think so. But when you look at the model behavior, in this case is the work from Phil, Jim and Lockie and Neil, I think, recently, evaluating the VESTA model against the independent data, most of it here Aquarius data, and then wildfires. For the wildfires, or for the experimental fires, we have an error of 35%, and for the wildfires, 54%. So a bit more uncertainty in wildfires, as you can expect, because in the experimental fires, you measure wind, you measure fuel moisture, you know the fuels. Here, you need to estimate all those quantities, so there's higher uncertainty in the inputs, and you get a bit more of error. But what's very interesting in this graph is that the idea that a lot of people have is if you develop a model from this is going to underpredict this. But when you look at the data, there's no underprediction bias. Right? In fact, there's a bit of an overprediction bias again because of this data point. There's another data set where you can do this paired analysis, so the same model compared to experimental and wildfire. It's a model for crown fires in North America. And again, very similar statistics. This is an international crown fire modeling experiment in Canada. The model for this predicted with an error of 26%, and for the wildfires, both in the US and Canada, with 52%. So again, it's the same issue, but interesting that the errors are very, very similar. Linked to this question is also this other question on are crown fires more difficult to predict than surface fires, right? Again, because that's cool, big fire, a lot of unpredictability. We rank all the studies by the mean absolute error. Here just have a snapshot of the 49 studies. We see that some of the crown fire model evaluations, the orange ones, one is pretty much on the top ranking area, and then the other one's in the middle of the table. And all the large errors came from surface fires, right? And the reason here is because when you have a ground fire, it's essentially wind speed and fuel moisture. So it's pretty much just two variables driving fire propagation. When you have surface fires, you have a much larger fuel effect. And so now identify fuel at scale that's affecting the fire leads to much larger errors. Obviously, in terms of error, a large error for a crown fire has much larger implications than a large error for a prescribed burn, right? Another thing we saw was interesting from this study with all these data points is this this issue of an exact prediction, right? And Jack Kepper, in the first day, mentioned that the only certainty about the prediction is that prediction is not going to be right? Something like that. And you see a few studies, tend to develop models, and you like to see the right result, and sometimes you see really very accurate predictions. And well, how often does this occur? That was our question. Another way to answer these questions, you also need to decide what's an exact prediction, right? Because it depends on the scale we are looking. Just in the example, if you have the same quantity in meters per second, 2 kilometers per hour, depending on the digits you use, it varies, right? So it's a bit subjective. For this study, what we did is that let's consider, because there was no standard to say what's an exact prediction, we considered an exact prediction is where error is less than plus or minus 2.5%. So you put a band of 5% around the observed rate of spread. Excuse me. And so when you look at the data, only 3% of the predictions, 35 of the 13 under, were considered to be exact predictions. So very, very difficult to get. It's more, you get an exact prediction just by chance, not because of model adequacy or user savviness, let's say. Right. Then the other question, the last question we want to answer was this, what's acceptable error, right? If I build a model, is that good enough or not? Do I need to do more? Or I'm satisfied with it. Again, there's no standard to what to be considered an acceptable error. Partially also because what's an error depends on your risk, how you see risk. Some users might consider are more strict in terms of what's an error, acceptable error. Others are more forgiving, let's say. And where the fire simulation is done, if it's in the urban interface or if it's in remote areas, right? Frank Albini, in the early days of fire behavior prediction, considered that a good error would be a factor of 2 or 3, so 200 to 300% over a range of magnitude of 2 or 3 orders. So fire goes from low intensity fire from 10 centimeters per minute to a wildfire 300 meters per minute. A few orders of magnitude. If you get an error of 200 or 300% would be good. Well, when you look at our data and looking into also some of the errors that we use in developing the empirical models, we took into account these aspects that the normal distribution, one standard deviation is about 34%, plus or minus 74%, right, Wendy? As some of the previous suggestions, and from our results, of course, we cannot come up with an absolute value. There's no method to do that. But given what we saw with what was said before, we came up with this threshold of plus or minus 35%. Again, because nobody did it before, we said, oh yeah, let's just throw a number out there and see what happens. So that's what we consider to be, if you get such an error, is a reasonable and conservative standard for model performance. Some take-home messages. Again, high intensifiers are not necessarily more difficult to predict than low intensifiers, right? As we saw from some of that data. Another one that I have quite an interest is that when you talk about fire modeling, there's the empirical models and the physical models. There's like these mantras that come say empirical models are only valid for the data sets they were developed in, and physical models are valid for everything, right? But what we saw from this evaluation is that the empirical models are well developed, are developed with considering relationships that have been shown to work. We have been able to extrapolate the models way out of the original data sets, and the models are working, right? So that's what the data says. And this 75% error is what we constitute an acceptable error. The last slide is some words of wisdom from Marty Alexander. Some people like to wait for better models and improvements that science will going to deliver for us to better predict fire behavior. But what it says is that these improvements are more likely to come from individual self-improvement, using the best available models and local case study work and adaptation, rather than expecting for fire scientists to deliver new models. And this local case work goes back to what is taught in these FBAN courses, and Phil mentioned yesterday. Back in the day, we used to do a lot of case study work, look at fire behavior in its natural environment, let's say, and we don't do so much of that anymore. But that's where we're going to really get a best understanding of fire and improve our fire simulations. And yeah, that's the last slide I have.